Good morning, everyone. Today we are diving into extremely useful topic for us: deep learning, AI, machine learning. What is Capsule Network (DL) in more markets? We are starting. Generative AI is a tool and service of humanity. What is deep learning? Deep learning is a subset of machine learning method based on artificial neural network with representation learning. The adjective deep refers to the use of multiple layers in the network. Methods used can be either supervised, semi-supervised, or unsupervised. Like AI and machine learning, deep learning has been kicking around in research for decades. What's changing in that it's being added into many types of chips, from data centers to simple microcontrollers. And as algorithms become more efficient for both training and inferencing, this part of the machine learning AI continuum is beginning to show up across a wide spectrum of use models, some for very narrow applications and some for much broader contextual decisions. Some of this is in anticipation of what will be required in chips for autonomous vehicles, said Chris Raven, CEO of Bub Labs. Techniques with neural networks are working, and the cost in terms of power is pretty modest. So it makes sense to add deep learning subsystems. We are seeing a lot of startups coming into this market. There are 25 in the deep learning space alone. Some are oriented towards the cloud, where they hope to knock out NVIDIA, for example, but some are in the low end of the market too. In both cases, there is a recognition of a very specialized idiom of computation for matrix multiply that is highly structured, but where you need low to medium bit precision that's as fast as possible. And there is an almost unlimited appetite for compute power. That bodes well for variety of tools, chips, software, and expertise to make this all work. Despite all of this, the definition of deep learning remains a little fuzzy. It sits under the artificial intelligence umbrella, either alongside machine learning or as a subset. The difference is that machine learning uses algorithms developed for specific tasks. Deep learning is more of a data representation based upon multiple layers of a matrix, where each layer uses output from the previous layer as input. The approach more closely mimics the activity of the human brain, which can tell not only that a baseball is in motion, but approximately where it will land. Yet behind all of this, there is no consensus about exactly how deep learning works, particularly as it moves from training to interfacing. Deep learning is more of mathematical distribution for complex behavior. To achieve that representation and to shape it, there are a number of architectures being utilized. Deep neural networks and convolutional neural networks are the most common right now. Recurrent neural networks are being used as well, which adds a dimension of time. The downside of RNNs is the immense amount of processing, memory, and storage requirements, which limits its use to large data centers. Geoffrey Hinton, a British computer scientist and cognitive psychologist, also has been pushing the idea of capsule networks, which stack up layers inside of layers of neural network, basically increasing the density of those layers. The result, according to Hinton, is much better because it recognizes highly overlapping digits. And this is one of the themes that runs through much of the research today, how to speed up this whole process. The problem is so complex that it's very beyond the capability of the human brain to figure out everything. So all of this has to be modeled or theorized. For chip makers, this is nothing new. Ever since chips reached the 1 micron process node, it became hard to visualize all of the different pieces in a design. But in computer science, many advancements have been largely two-dimensional. Rotating or tilting objects is much more difficult to represent mathematically, and that require a lot of compute resources. In the interest of speed and efficiency, researchers are trying to figure out ways to prune those computations. Still, it's a big challenge and one that's largely opaque to deep learning experts. Deep learning, in part, is a black box, uh, which said Michael Schuldenfrei, CTO at Optimal Plus. It's difficult to understand the actual decision making. You can explain the model that the machine learning algorithm came from. We do a lot of work comparing different algorithms. The deep learning algorithm is more complicated than machine learning algorithms. But one thing we have found across of them is the answer derived from those algorithms may be different across different products. So on product A, random forest works well. On product B, another algorithm or combination of algorithms work better. Deep learning algorithms date back to the late 1918s. A lot of this work started with the US Post Office, which needed to recognize handwritten digits, which said David White, distinguished engineer at Cadence. They realized they needed a way to decrease the size of the input space, so they used additional layers to extract features. Since then, there have been a lot of advances on deep learning algorithms. Deep learning algorithms typically need a lot more computational horsepower than machine learning. The architecture used in deep learning is specific, said White. It uses convolution, pooling, and specific activation functions. Some of the techniques are similar to machine learning, some are different. Not everything benefits from this approach, sir. The nature of more parameters is that you can model very complex behavior, said Bob Labs Rowan. But you have to train it with corresponding data set. If you take a simple problem, a deep neural network is not more accurate. Statistical modeling can only go so far. Humans can learn a whole bunch of things about objects and how they move when you rotate them. That built into human brains with favor examples. That current machine learning or deep learning examples. But today, machine has no notion of when you rotate an object. It doesn't know perspective. It only can learn from enough millions of examples. Right now, let's talk about deep learning in more markets. Yeah, why the demonstration one. Those points for deep learning and machine learning aren't always clear, the application of those different slices are coming into focus. Deep learning for embedded vision is well defined, which said Gordon Cooper, its product manager for Synopsys. Embedded Vision Processor Group. We're also seeing it being used for radar and audio, where you apply a CNN algorithm to it. And we are seeing a lot of requests regarding IT processes and applying deep learning and AI to those. What makes this technology increasingly accessible is the ready availability of technology building blocks, including off-the-shelf algorithms and a variety of off-the-shelf and custom-built and semi-custom processors, accelerators, and chip memory. With RNNs, you are looking at a lot short-term memory, said Cooper. Its power isn't an issue. You can use a GPU. There are also chips where you get less performance and focus instead on power and area. Bandwidth remains a big issue, particularly how you get data to and from DRM. So inside the chip, there are memory management techniques and multiple accumulate. Chip companies already are getting some first-hand experience with technology by using it internally as well. We use machine learning today to manage our compute farms for I/O throughput, which is pretty challenging, said Silicon's Jan Fagna. We track all of the GPUs and calibrate them against the jobs and create predictive loads. It's basically predictive load balancing, and much of that is done in software. Cloud companies like Google and AWS, Amazon Web Services, use deep learning for their workflow and load balancing, and they use hardware for that. Deep learning potentially is the most silicon intensive piece of those operations. One of the newer applications of this technology involves robotics. The key there is then these devices need to continuously learn because the task a robot does changes and different environments can change. So, if you are manufacturing in the Philippines versus Europe, for example, the software may have to adapt. It's the same for a lot of the IoT. Sensors go into systems in very different environmental conditions. This requires adaptive systems, which will be the next big wave for machine learning. Deep learning as well and AI. For a gas sensor monitoring different wavelengths, as the sensor degrades, as signals change. So the question is whether a system can adapt to that kind of change and still do their job. You don't want to shut a system down every time you get condensation on a camera lens. Deep learning is showing up in mobile phones as well. Apple's iPhone X uses deep learning for facial recognition. You also can use it to improve the picture on a mobile device, applying filters based on deep neural network techniques. But each of those markets have its own needs. So, for cancer detection, the challenge is getting enough data points. Tens of thousands isn't enough. The reverse is true in automotive, where you have hours of video, but what do you do with all of the data? The key there is how you use technology to find a section of this video that's important. This industry is just beginning to scratch the surface of how deep learning can be applied effectively and to understand where it does and does or does not add value. From there, it will be a scramble to figure out how to do the necessary training and interfacing more quickly using the least amount of power. In the past, this technology was closely linked with mainframe computers and supercomputers. But as it gets parsed into smaller pieces for more limited applications, deep learning will have a much bigger impact across a growing swath of markets. The run up of those markets is just beginning. We are finishing for today. If my video was useful, put your like, subscribe this channel and stay on AI side. Thank you for today.